Welcome to the video, Method of Lagrange Multipliers, Part 3. We're going to look at an optimization problem with two constraints, such as maximize a function f of x, y, z, and we'll have constraints on what x, y, and z can be. Some function g1 of x, y, z will have to be 0, and some other function g sub 2 of x, y, z will also have to be 0. So in this video, we're going to look at maximizing or minimizing a function of three variables subject to two constraints. To illustrate the method that we're going to be adopting, we will consider the following problem. Find the dimensions of a rectangular box with dimensions x, y, and z, length, width, and height, that maximizes the volume. X, y, and z must also satisfy the following constraints. First, the surface area of the box must be exactly 150 square units, whatever unit we are using for measuring lengths over here. And secondly, the sum of the edges, the length of the edges, 4x plus 4y plus 4z, must be 100 units. If you think about this box, there are four sides here, here, over here, and here of length x, so that explains the 4x. Similarly, there are four edges of length 4y, and four edges of length z. So we want this sum of lengths to be 100 units. So we'll consider the following optimization problem. We want to maximize x times y times z, which is the volume of that box. And let's call x times y times z the function f of x, y, z. We are also going to have constraints. One constraint on the surface area and another constraint on the sum of all the edges. The surface area is 2xy plus 2yz plus 2xz, and the constraint was that has to equal 150 square units. The sum of all 12 of the edges is 4x plus 4y plus 4z, and our constraint there is that this quantity has to equal 100. So we have for the constraints a constraint on the surface area and the sum of the edges of this box, the edge lengths. Now, we're going to rewrite this just slightly. We'll use this maximization statement exactly the way that it is here. But for the other two, we want to write the constraints as something equals 0 and something else equals 0. So we look at this first constraint up here. We can subtract 150 from both sides. So that'll give us 2xy plus 2yz plus 2xz minus 150 equals 0. Let's call this function of x, y, and z g sub 1 of x and y and z. Similarly, the second constraint, by subtracting 100 from both sides, g sub 2 of x, y, and z is going to be 4x plus 4y plus 4z minus 100, and we also want that to equal 0. So the general problem is to maximize or minimize some function of x, y, and z, and we have two constraints that x, y, z must satisfy. So how do we approach this using the method of Lagrange multipliers? Well, we will introduce a new function which I'll call capital F. Capital F is going to be a function of x, y, z, and two Lagrange multipliers, lambda sub 1 and lambda sub 2. Since we have two constraints, we'll have two Lagrange multipliers. So this new function is going to be little f of x, y, z, which was the function we're trying to maximize, plus lambda 1 times that first constraint function, g1 of x, y, z, plus lambda sub 2 times that second function, g sub 2, which came from this second constraint. So now that we have defined this capital F, what do we do with it? Well, the local maxima and minima of this function here occur at the points satisfying the following. Notice that this is a function of 5 variables, and we have 5 equations here all of which have partial derivatives on the left-hand side and 0 on the right-hand side. So looking at these variables x, y, z, lambda 1, lambda 2, we have the partial of f with respect to x equals 0, the partial of f with respect to y equals 0, the partial of f with respect to z equals 0, the partial of f with respect to lambda 1 is 0, and the partial derivative of f with respect to lambda 2 is also 0. So what we have here basically are 5 equations in the 5 unknowns x, y, z, and the Lagrange multipliers lambda 1 and lambda 2. For our rectangular box problem, we're trying to maximize the volume f of x, y, z equals x times y times z, and we have two constraints. One on the surface area of the box, and we'll write that as 2xy plus 2yz plus 2xz minus 150 equals 0, and call this function right here of x, y, and z g1 of x, y, z. Similarly, the other constraint on the sum of the edges we can write as g2 of those coordinates is 4x plus 4y plus 4z minus 100 equals 0. Now, here we know what g1 and g2 and f are, so we can define our function, which we called capital F, the following way. It's going to be little f plus lambda g1, lambda sub 1 g1, plus lambda sub 2 g2. And we know what f is, what g sub 1 is, and what g sub 2 of xyz is. So we'll just substitute those in, and we have f of xyz lambda 1 lambda 2 is the little f function, which is xyz, plus the first Lagrange multiplier lambda 1 times the function g1 plus lambda 2 times the function g sub 2. Okay, so here's our function capital F, and what we need to look at is the equations that these partial derivatives all equal 0. Let's look at the first equation, partial of f with respect to x, and let's see how we got that. The partial derivative of this term with respect to x is just yz. The partial derivative of lambda 1 times this stuff, if you differentiate this stuff with respect to x, you're just going to get lambda 1 times 2y plus 2z. And so we can write that as 2 lambda 1 times the quantity y plus z. And then, if we look at the last term, the partial derivative of this term with respect to x is just going to be 4 times lambda 2, which we have here. So we get yz plus 2 lambda 1 times y plus z plus 4 lambda 2 equals 0. Evaluating this second equation, we get xz plus 2 lambda 1 x plus z plus 4 lambda 2 equals 0. Looking at this third equation, differentiating with respect to z, we get xy plus 2 lambda 1 times x plus y plus 4 lambda 2 equals 0. When we look at the equation, the partial of f with respect to lambda 1 equals 0. This term doesn't have lambda 1 in it, so its derivative is just 0. This one, if you differentiate this with respect to lambda 1, you're just going to get 2xy plus 2yz plus 2xz minus 150, and that's this stuff right here. And when you differentiate this last term with respect to lambda 1, there's no lambda 1's in this term, so that's 0. So this equation just gives us that constraint equation. Similarly, if you look at the partial of capital F with respect to lambda 2 equals 0, that just gives us the other restraint equation. So we have 5 equations and 5 unknowns here, and we are going to take the easy way out. We will solve this system of 5 equations and 5 unknowns by using SageMath. Actually, we'll use SageMath to do the entire computation including finding the partial derivatives, finding these equations, and then solve. So let's see how we can do this using SageMath. The first thing we'll do is define capital F of x, y, z, lambda 1, lambda 2 to be the stuff that we saw before. That is done right up here. Let's take a look at it. F of x, y, z, L1, L2, that's what I'm going to use for lambda 1, lambda 2 in this program, is equal to all of this stuff right here, which is basically this expression. And then afterwards, we'll just show what f is so that we can see if we typed it in right. And so when we execute this statement, the output is this line here. So what does this function capital F do? It takes x, y, z, L1, L2 into x, y, z plus 2 times this stuff times L1 plus 4 L2 times this stuff. Okay? If you want, you can check each of these. The stuff that's multiplied by L1 here, this stuff right here, is just what we have right up here. This stuff 4 times this stuff over here is multiplied by L2. 4 times that stuff is right here, multiplied by lambda 2. So we just wrote it in basically the way that this equation is, but SageMath itself did a little bit of rearranging, but they are equivalent. Okay, so next thing we want to do is evaluate the first order partial derivatives of the function capital F in order to write down a system of equations that must be solved for the critical points. I noticed that we have a slight misspelling here, double S. I guess that's okay in German for some words, but not in English. So let's see what we have here. These are basically the derivatives. EX is the derivative of capital F with respect to x. EY is the derivative of capital F with respect to y. Capital F, remember, is this function up here. EZ is the derivative of f with respect to z. EL1 is the derivative of f with respect to L1. EL2 is the derivative of f with respect to L2. So in our regular mathematical notation, here we're differentiating f with respect to the Lagrange multipliers, which we called before lambda 1, lambda 2. But in this program, we're calling them L1 and L2. So then after that, we want to see if the derivatives were calculated correctly. And so we'll show each of those, show EX, show EY, all the way through show EL2. And so that first derivative takes x, y, z, L1, L2 into this function. This second derivative, which we stored in EY is this function. It takes this tuple of 5 parameters and returns this as the output. Similarly, for the derivative of f with respect to z, L1, L2, they're down here. And if you want to, you can go back just a little bit to the previous slide, I guess, and check. These are what we got by our hand computation earlier. So basically, looking at these partial derivatives, we want to set each of those equal to 0, which we did here. And then we want to solve for x, y, z, lambda 1, and lambda 2. Actually, the only things that we're interested in here are x, y, and z. So if we can find them without finding lambda 1, lambda 2, that's okay. But we're going to find them all by using SageMath software. So now we're ready to set each partial derivative equal to 0 and solve the system of 5 equations and 5 unknowns. So let's look at this command in SageMath. Solutions equals solve, and then we have 5 equations, and then we're solving for the variables x, y, z, L1, and L2, and then semicolon for that command to end. And then we called the set of solutions SOLNS, my short for solutions. And so here we just print out the value of solutions. It'll print out what is stored in this variable. So when we execute this, before that, let's look at this. EX, remember, was the partial of capital F with respect to x. So the partial of f with respect to x equals 0, the partial of f with respect to y equals 0, all the way through the partial of f with respect to L2 equals 0. L2 is what we called lambda sub 2 when we were writing out the mathematics. And we're, as I mentioned, trying to find the values of x, y, z, L1, L2. And so here's the value of this variable, solutions. The first, so this is a list of lists. And in our list, the first list is x equals minus 5, y equals 15, z equals 15, L1 and L2 equal these numbers. And then the second solution is x equals 65 thirds, y is 5 thirds, z is 5 thirds, L1 and L2 have these values all the way through here. I guess there are 6 solutions total to the system of equations. Now some of these are not really feasible physically. For instance, we cannot have the length of a side x being minus 5. So this first solution to that system of 5 equations, 5 unknowns, is not going to be a solution to our rectangular box problem. So we're going to have to do something more to figure out which one has the maximum volume. And so for each solution that we have up here, let's find the volume corresponding to it, f of x, y, z, which remember is x times y times z. So here's what we can do. We're going to have a loop here. For k in the list 0, 1, 2, 3, 4, 5, we're going to let x equal solution sub k 0, y equals solution sub k 1, z equals solution sub k 2, area is x times y times z, and print the value of x, y, and z and area. So what is happening here? Well, solution sub 0 here is going to be this element right here. In SageMath, arrays start with index 0. And now to get the value of x, that's the 0th element in solution sub 0. And so for this first one, maybe I should say this 0th one, this 0th solution, the x value is in the 0 place of that 0th solution. Similarly, the value of y up here is in the first place in the 0th solution, and then z similarly, and then we calculate the area and reprint it out. So here is what we get. The first solution gives us I should have said volume here, I guess. The volume is minus 1125. That can't be right. No, let's put it this way. It is a solution, but it's not a solution to our physical problem. Can't have a negative volume and also a negative side length. The next solution gives us a volume of 1625 over 27. Another negative volume for this one. This one, same number, 1625 over 27. 1625 over 27. And this last one, the values of x, y, and z turn out to give us a volume of minus 1125. Okay, so basically we look at this and we have these three being the maximum volume, And if you look at each of those, we have two sides of length 5/3 and two dimensions 5/3, and the other dimension is 65/3 in all of these. And so that tells us that the maximum volume occurs when the three dimensions of the box are 65/3, 5/3, and 5/3. Well, this kind of wraps up this video. I hope that you found it instructive in two ways. Learning how to use Lagrange multipliers to maximize a function of three variables. And in part 3, we had two constraints. If you go back to part 2, there was one constraint. If you go back to part 1, we were looking at functions of two variables with one constraint. So we've looked at three important cases of the use of Lagrange multipliers. So hopefully you got something out of these videos. Hopefully you also enjoyed them, and stay tuned for hopefully more videos in the future.